Time for a new topic. Checking out topic 4. And we are intentionally starting with lesson 4.2, so don't worry about 4.1. But do make sure that you have taken the chance to pull up your bell work and complete that here in these two boxes. So your bell work will be in Schoology, but you can show your work for those problems here. So our topic for 4.2 is we want to explore rational numbers a little bit. So our whole learning goal is to describe characteristics of irrational numbers. So your learner's question could sound something like, what are the characteristics of irrational numbers? Something along those lines. But I will let you personalize that yourself. So as you fill in this top part of your notes section, we're going to be looking at different categories of numbers. So natural numbers, which I usually think of just as our counting numbers like you learned in preschool. Whole numbers, integers, rational numbers, irrational numbers, and real numbers. So you are going to use the information from this table I'm going to show you to help fill this in. You can list examples and write your own definition here as I talk you through. So when we think about our number system, let's start with our smallest set, which would be our natural numbers, our counting numbers. Like I said, those are the numbers that you learned in preschool. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you'll notice that I don't have to represent them in counting number form. For example, last topic, we're looking at square roots. Well, the square root of 25 is 5. So this has a value of 5. So even though it's not written just as the numeral 5, because it can be simplified to 5, this is considered a natural number or a counting number. Same with 4 halves. 4 halves simplifies to 2, so it's a natural number. My next category up, just a step bigger, is whole numbers. So whole numbers are all of my counting numbers plus 0. My next category is integers, which are all of my counting numbers and 0, and all of the opposites of my counting numbers. So anything that can be written as a whole number or its opposite, or the negative version. So -3, -10 fifths. Again, this would simplify to -2. And the opposite of the square root of 16 would be -4. So this would count as an integer. My next category up is rational numbers. So rational numbers are numbers that can be written as a ratio or as a division problem. So A over B. So -2/3 can be written as a ratio or a fraction. So -2 divided by 3. So it is a rational number. 25 hundredths as a decimal. This can be written as a fraction or a ratio. I could write it as 25 hundredths. So this is rational. So notice integers, whole numbers, and natural numbers are all part of rational numbers. So the only new thing we've added here that is rational but not an integer, whole number, or natural number would be my fractions and decimals. So this is one big category with lots of subsets. The opposite of rational numbers would be irrational numbers. So this is a different set that does not meet any of these criteria. Irrational numbers are numbers that cannot be written as a ratio or as a fraction. So for example, the square root of 10, if you punch that in on your calculator, you're going to get a decimal that goes on and on forever without repeating. That makes it irrational. Anytime we have a decimal such as this that goes on and on without repeating, we automatically know it's an irrational number. The most frequently known irrational number is pi, because pi is a decimal that goes on and on forever without ever repeating. And anytime I take the square root of a number that's not a perfect square, I'm going to get a decimal that goes on and on forever without repeating. Thus, it is irrational. Now, you might be looking at this decimal and saying, well, there's a pattern. Don't be fooled. It has to be a repeating pattern. My pattern here is 0, 1, 0, 0, 1, 0, 0, 0, 1. So there is a pattern to these digits, but it's not a repeating pattern. Only repeating patterns would be considered rational, such as negative 2/3. As a decimal, this would be negative 0.6, and the 6's repeat forever. That's a repeating pattern, so that is rational. But any decimal that does not end and does not repeat is irrational. So you can go ahead and add those notes in your own words. And now let's practice classifying some of these numbers. So let's decide if the square root of 4 is rational or irrational. So remember, the only square roots that will be rational are the square roots of perfect squares. If I take the square root of a non-perfect square, it's going to be irrational every time. So let's make a little cheat sheet and help ourselves out here, and let's list all of our perfect squares. Remember, my perfect squares is when I take my counting numbers and I square each one. So 1 squared, 1 times 1 is 1. 2 squared means 2 times 2. 3 squared is 3 times 3. 4 squared is 4 times 4. 5 squared is 5 times 5. 6 squared is 36. 7 squared, 8 squared, 9 squared, 10 squared, and so on. You get the idea. So the square root of 4, 4 is a perfect square, so I'm going to get a whole number when I take the square root of 4, so it is rational. The square root of 3, 3 is not a perfect square, so its square root is going to be an irrational number. 5 is not a perfect square, so its square root will be irrational. 7, not a perfect square, so the square root of 7 will also be irrational. 2, don't be fooled. 2 is such a nice even number, but it is not a perfect square. It is the square root of 4, but it in itself is not a perfect square. There's no one number I can multiply by itself to get 2. So when I take the square roots of a non-perfect square, I'm going to get an irrational number. 8 is a lovely number whose cube root is 2, but its square root is an irrational number because 8 is not a perfect square. 9, however, is a perfect square. The square root of 9 is 3, so that's rational. The square root of 6 is irrational because 6 is not a perfect square. All right, let's check out which of these numbers are irrational. The square root of 25, the square root of 50, the square root of 125. If you said the square root of 50 is irrational, you are correct. The square root of 25 is 5, so that's rational. And how about the square root of 125? We've gotten pretty familiar with this number. And if we were taking the cube root, it would be rational, but if I'm taking the square root, it is irrational because I don't have any number multiplied by itself that will equal 125. 11 squared is 121, 12 squared is 144, so this would be irrational as well. All right, let's check out some patterns. We're looking at decimal expansions, and we want to know which number is not irrational. So let's look at each of these. On number 1, I have 3.20, 200, 2000, 20000. So I definitely have a pattern, but is it repeating? If it's not the same exact pattern over and over and over, it is irrational. On number 2, I have 3.213, 213, 213, 213. So I see a series of 3 digits repeating over and over. So this one would be rational. Decimal number 3, 3.12, 122, 1222. Again, I'm seeing a pattern, but not a repeating pattern. So the only one that is not irrational would be number 2 here. All right, a little more practice with rational, irrational. They ask you to assume that each pattern continues. So when you see the dot, 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 that means whatever pattern comes before these dots is going to continue. I don't know why they chose not to use the repeating bar, but if you see the dot, 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 assume that the repeating digits continue repeating. So 2.125. I see that this decimal has a clear end, so I'm calling rational. On letter B, 2.1111, and it looks like it continues forever. I know that as long as it repeats, it is rational. Letter C, 2.01, 011, 0111, 01111, a definite pattern. I'm increasing the number of ones each time, but it's not a repeating pattern, so it's irrational. On letter D, I see a repeating pattern. The 1, 2, 3, 4 is repeating, therefore it is rational. And on letter E, 1.80333, and I can see that the 3 is going to repeat, therefore it is rational. All right, finally, to wrap it up, let's practice categorizing different numbers here. So let's start with 15. 15, I would say, is definitely a natural number. When I was in preschool, I learned how to count to 15. So that's all my counting numbers. It's also a whole number because my whole numbers are my natural numbers plus 0. It's also an integer because it's a whole number and a natural number, which means it's also a rational number because I could write this as a ratio or a fraction. If it is rational, it cannot also be irrational because these are opposites of each other. So it's rational, therefore it is not irrational. But it is real. Real numbers are every number I have ever learned. Up until this point in time, we have not learned about imaginary numbers, which is the opposite of a real number. So everything that you know, every single number you know of, is a real number at this point. We don't know about imaginary numbers yet. Let's check out this decimal here. Since I see that it's a decimal and it's negative, I know it's not a counting number. I certainly did not learn this in preschool. It's also not a whole number, and it's a decimal, so it's not an integer. However, it's a decimal that ends or terminates, so it is rational. I could write this as a fraction. It's rational, so it's not irrational, and it's also real. The square root of 45. 45 is not a perfect square. So when I take the square root of this, I'm going to get an irrational number because it's going to be a decimal